Hello? Okay, great. So good morning, everyone. So it's my pleasure this morning to talk to you on the subject of rack-scale computing. I'm Ant Rowstron. I come from Microsoft Research in Cambridge in the UK. I think this is a sort of great gathering where we have these sort of ideas of how research and business interact. Coming from an industrial research lab, I guess I have the luxury of having one foot in the academic world and one foot in the industrial world. I have to give a warning that what I'm talking about today is sort of the ramblings of a madman rather than Microsoft's view of the world. So you must bear that in mind as I talk. Now, rack-scale computing. About 7 or 8 years ago, I got very interested in how we were going to build out the underlying infrastructure for the cloud. And at the time, there was a really big push by the big players, the Googles, the Amazons, and the Microsofts of the world, to think about what the unit of deployment for cloud computing data centers might be. And at the time, it was really common to think about shipping containers. So these are the sort of storage containers that you'd see on the back of a ship that was going across the Atlantic or whatever, transporting goods. And the idea was that you should pack this shipping container full of hardware and then just drop them, probably many of them, perhaps even on top of each other, to form and build data centers. And so there was a sort of feeling that this shipping container was becoming the unit at which you would deploy the data center. Subsequently, shipping container-based data centers haven't really taken off. However, it's been a very stimulating process of thinking about, well, what is the unit? And today, and there's a big hint in the title, I'm going to talk to you a little bit about how we think about the unit of deployment, the rack, and I'm going to talk to you about some emerging hardware trends. And I think what's really interesting is these emerging hardware trends sort of started off a few years ago with startups and with odd people doing odd things. And in the last 18 months to 6 months, we've seen a big uptake of this in much of industry. And I think, hopefully, when I explain to you some of the hardware trends, you'll understand why we're now interested in thinking about how we build racks. Once I've talked about that, I'm going to think a little bit about, well, okay, so there might be this new unit, there might be this new change in hardware, but how will it impact the software that runs on top of that platform? And I'm going to give you a little view of some of the work we've been doing, looking at what the impact on the software might be. So, I'm sure that most of you have probably heard of the Facebook sort of inspired open compute project. Now, this is something where the big players like Facebook, Microsoft, Amazon, Google, they're all sort of in the stage now where they're really thinking about how they build and design their hardware that they deploy in their data centers. And Facebook sort of said, well, let's start this open compute project and let's sort of open source all the design work we're doing. And so the first really high-level question might be, well, why are organizations like Microsoft's and the Facebooks and the Googles of the world really interested in thinking about the hardware? Because traditionally, you know, a software company who was deploying a data center would have a rack. They would go out to a Dell or an HP or another manufacturer, and they would buy units that they would slot into these racks. And it's really simple. And I think this one part here really highlights it, which is when you are building out really large data centers, and you are building out a large number of them, and you are putting in tens or hundreds of thousands of racks, you're becoming at the scale where if you can improve the efficiency of your hardware or lower your cost of operating per rack, then this has a significant impact on you. And here, for example, Facebook have said that their servers are 38% more efficient and 24% less expensive to build than what they call the vanity types of servers, the servers built by the other manufacturers. And so this is sort of the bit which is starting, I think, to really show how people are thinking. And just to sort of give you some context and step back, now if we think of where we are today and then think where we will be in 5 years, I think the key thing is going to be this notion of converged design. So at the moment, you have something like a rack. And even with something like the Open Compute project, you still think about it like this. And then what you have is a series of units. We often call these 1U or 2U. So a rack is sort of so high, and you're deploying units that are about so big, and you're slotting them in. And what the Open Compute project is really trying to do is saying, let's think what the infrastructure, what the rack looks like, and let's think about what each of those modules looks like that we plug in. So a module might be a high-end server with large amounts of memory. A module may be a set of disks in a unit that you plug in. And within the rack, you have the infrastructure built into it to then let those modules communicate and talk with each other. Now, where I think we're really heading, and as I talk to you about some of the changes in the hardware, you'll begin to understand why I think that this is the way forwards, is to move to a model where you just think of the rack as a unit. When you are deploying racks, why think in units that are 1U or 2U? You surely just think of a unit which is effectively 42U to 52U, depending on the size and the scale of the data center. Now, once you start down this path, what you begin to do is to think, well, if I'm going to build a 52U or a 42U rack, I might as well go back and rethink everything and effectively co-design everything together. So you've got things like the mechanical side, you've got the power, you've got the cooling, you've got the hardware and the system configuration, and you've got the software. And what happens, and we've now built in Cambridge at least one rack to do storage, where we've taken this as the sort of the starting point, where we would rethink everything. What happens is you sort of radically pare back the costs and the operating expense of operating that rack. Now, today, I'm going to focus a little bit on two things, which is the software and the hardware. So I'm not going to talk anything about power, cooling, or the mechanics. If you're interested in that, then it's a great area. But today, I'm going to really think a little bit about the software and the changing hardware. And in particular, I'm going to think about this boundary between the two, because I actually think it's the most interesting point when you begin to look at these racks and think, right, how are these changes in the hardware, the power, and the cooling going to come through to the software? So I want to now, I've given you a little bit of context, I want to now just step back slightly further. And I want to think, if I'd been giving this talk 2 years ago, what I would have been saying to you. Well, I first of all would have been saying to you, the first big change is in the data center world and in the server world, up until now, there's effectively been one company producing the processors that we're using, Intel. I don't know how many of you own servers, but I would be willing to bet they all run Intel processors. But then back in about 2011, something happened, which was ARM said, well, we're now going to produce a 64-bit processor. So traditionally, ARM produces 32-bit processors. And of course, we all know ARM because we all carry a smartphone, and these smartphones run in them ARM processors. And the really great thing about ARM processors are two things. One, they're really low power. If you think what they do in this form factor without a fan, it's spectacular. The other thing is that the actual processor in here is not made by ARM. It's actually made by someone like perhaps Qualcomm or another manufacturer. And what those guys do is they take cores that ARM describe and they build IP. They put other circuitry on the same silicon to build a sort of chip which is useful. So this has two effects. One is that you're going to get, if ARM come into this space of servers, you're going to get really low power and therefore higher density compute. The second one is that people can start to innovate in technology that goes into the cloud. So now a company like Qualcomm or a company like Applied Micro or anyone else can go out and get a server class core and begin to put bits of technology around them on the same silicon that they think will be interesting. Now, one of the earlier players in this space was a company called Calxeda. And in 2011, Calxeda started to produce ARM-based chips. At that time, 2 years ago, they were 32-bit processors because they were sort of gearing themselves up to what they'd be able to do when they could go out and get a server-class chip. And I'm going to talk a little bit more in the next slide exactly what the Calxeda guys did. But there's two things to say about them. One is that they put a lot of IP, a lot of new functionality on the chip destined for the server. The second one is they were ahead of the game and they've gone bust, so they no longer exist today. But I think what they did do was begin to show where we would move. And in fact, we're now beginning to see the 64-bit server-class chips coming online. And in fact, in April 2012, Applied Micro, I think, produced the first ARM 64-bit processor. The HP Moonshot in November 2011 was a project that HP were doing. And they said, well, if we're going to get lower power and we're going to get cooler processors, we can start to really think about how we increase the density of compute in per unit. And they were building out in 2011 units which were sort of 4, 5, 6 U high, which were, by standards of what was deployed then, incredibly high density of processors in it. At the same time, you saw companies like Intel going out and buying the interconnect business from Cray, and you saw AMD buying a company called SeaMicro, and SeaMicro were also building out 8U, so this is, you can see the box at the top there, that's a SeaMicro chassis. That's about 8U. It has, if I remember correctly, 64 processors in it. And it is designed as a unit, and it uses a very special interconnect with inside the SeaMicro box to enable processors to communicate with each other inside them. And so let's explore that a little bit more. I want to talk to you a little bit about the Calxeda SoC, because I think this is really showing you where things will probably go. Let me find the pointer. So this is a sort of schematic of the Calxeda chip. And what you see is basically they have here 4 ARM cores and some caches that you would expect in a memory controller. They have some energy core management, which helps them do energy management. They've got traditional controllers that you would expect on a chip. So SATA for disks, PCI Express for connecting other things. And they also have this thing, which is really interesting. This is called the Energy Core Fabric Switch. Now, what it does, effectively, is it begins to distribute some of the functionality that we would normally associate with, say, a switch or top-of-rack switch in a rack into the processors. And I'll show you a bit more about that in a moment. But this is an example. So this was a unit you could go out and buy. It had 12 of these cards in it. Each one of these cards has 4 processors on it, like this. Interestingly, it's got its memory here. It's got 4 ports per processor for attaching disks, and you get basically 12 of them in the back of a standard rack. So that's 48 servers, and I can tell you that this is a 2U rack. So already then, they were getting 48 processors into a standard 2U rack. Now, if you scale this up to a normal rack, you're talking 900 processors. Now, if you think at the moment in a standard rack, you might have 1 network cable coming out of each server. So 1 network cable per 2 processors. What that means is you would end up with sort of 450 cables coming up to the top of rack switch if you use the same techniques that you use today to actually build the rack. So if you just said, Well, for each one of these two processors, I'll have a network cable that goes out, and I'll plug it in the top of rack switch. 1/3 of your rack will be top of rack switch. It just doesn't work. That's why this bit here was so incredibly important. And so effectively, what they did was they said, well, we'll just have 4 links, these little red arrows, to the outside world. And all these processors will talk to each other using a network that is internal to the box. And the network, I can tell you, has, from memory, 8 10-gig links per processor. 3 of those 10-gig links point inwards to the processors, and 5 of them are external. And those 5 links which are external are what you connect to create this sort of the network within inside the box. And that means as you push the density of these processors up, you don't end up necessarily increasing the number of links that you need to the top of rack switch. Now, the reason why they think this is really interesting is because, as I said, until this stage, it was very hard for a company to begin to think, well, what other technology would I like to put on the piece of silicon that I'm selling you? Until ARM started to say, well, we'll produce server-class chips, server-class processors, 64-bit processors. You weren't really able to have companies that could go off and think, well, I'm going to put a fabric switch on there, and I'm going to innovate in that space in order to actually help increase the density of drives. Now, I said to you when I started this is what I would have been saying 2 years ago, okay? And now, as I've already said, Calxeda have unfortunately closed down. However, you know, we are beginning to see the big players. So this is an Intel slide from a conference called Interop, where they show how they're thinking about this kind of space. And they show the sort of the traditional rack. They show where they're heading, called fabric integration. And then they talk about where they're going, which is when you begin, I think, to think of the design of the rack at a rack scale. So that's Intel. So I talked to you about the HP Moonshot, which I said was a sort of project that HP were doing to explore this space. You can go out and buy one of these today now. This is something that is out there. It's commercially viable. It's a very different. If you look at the chassis, it's effectively got a high density of cartridges, I think they call them, within the chassis. You can have 45 servers per chassis if you go for single server. If you go for quad servers, you can have 180 servers per chassis. Within the chassis, you end up with very, very different networks. Remember that I talked about the Calxeda and I showed you the network that they were running within inside their servers. Well, the HP Moonshot actually runs 3 different networks. One being a 2D torus mesh fabric, which it's used to talk to other servers within inside this box. One of them is a storage fabric, and the other one is the fabric for talking to the outside world. So, and this is viable today. You can go out and buy these now. So, let me go back to this picture. So I said to you, I really wanted to think today about this boundary. And hopefully I've given you a hint or a feel for how the hardware and the system design of servers could be changing. I think there's a real question about how much of this evolution and change do the apps that run inside the data centers see. Now, there's always a sort of tension between simplicity and complexity, right? And you know, in computing in general, we tend to use layers which hide complexity. So if I look at the moment at these boxes like the Moonshot boxes, like the Calxeda boxes that were available, like the C Micro boxes from AMD that are also available, they don't really expose the fact that they've got different networks, the fact that they're different. They just try to hide it all so it looks like a standard server. So, you know, I've used a C micro box. When you're using it and you're writing software on it, you're actually routing the traffic over a network which is a 3D torus kind of network, which is a very complex network with lots and lots of links in it. Yet it's exposed to you, and it feels when you're programming it as if you are using a standard top-of-rack switch to talk to these other servers inside this C micro cluster. And I think the challenge, as it always is how much do we expose? Why do we expose it? And you know, can we actually exploit it? And in a minute, I'm going to talk to you about an app that we've been building. I'm sure most of you are familiar with Hadoop. We've actually taken Hadoop and tried to look at how you would actually implement it on top of a platform that exposed much more of the topology information and the richness of the network within it. One of the big motivators for why this is an interesting question is because if we don't get the abstractions right and we don't understand how to layer our apps on top of these new infrastructures, there's a real chance that there's a cost and performance hit. So we will not be able to build racks as cheap as we could if we can't fully exploit them. If there are resources, networking resources, compute resources, storage resources within a rack that we're unable to light up because we haven't got the flexibility to really exploit that resource, then that will be a higher cost of using that particular box, which is why this is an important question. And as I say, you know, I think the in-rack fabrics, the way in which processors communicate, is one of the most interesting areas for me. My background is a sort of distributed systems and a networking guy, and that's how I got into this space, by thinking, what would these new topologies mean to the systems running on top of them? And for me, you know, if we end up with a world where TCP/IP, the thing that we use normally to communicate across a network, is used to mask the underlying network, then we will have really lost out. And I do believe that we need lower level APIs. Now, in Cambridge, we're doing quite a lot of work in this space. We've been working on in-rack fabrics for about 6 years. I'm going to talk about some of that work in a second. We've been looking at what it would mean to have different topologies in the data center. We've been looking at how you would expose the topology, how you would let people think about the topology, and I'll talk a bit about that. We've also been running a project in collaboration with some of our colleagues in Microsoft Research in Redmond, looking at how you would build out colder storage, so storage to store data which is touched less frequently. And we've been able to build out a rack which is about twice as high a density of storage as any technology that we know of today, and it does it at a price point which is very, very competitive, which means that, which I think begins to me to hint to really why the power of thinking of these designs and thinking about how we build things at a rack scale. Yes, so I'm going to focus mostly on this. So let me change gear now. So I've given you a bit of a view of the hardware. I've told you that I think it's really important to think about this boundary between the hardware and the software. Now I'm going to talk about CamDoop. And this was joint work with many of my colleagues, Paolo Costa, Austin Donnelly, Greg O'Shea, and many other interns. And the thinking behind this was, everyone loves Hadoop. Does anyone in here not know what Hadoop is? Okay, so everyone knows what Hadoop is. Hadoop is sort of the big data processing platform of the day. And I think the reason why everyone loves Hadoop is because it is a great high-level abstraction. You just sort of basically know Java and the MapReduce model. You know, it scales beautifully, it handles failures beautifully. It's ideal for unstructured data. And of course, it is inspired by Google's MapReduce. So what happens if we take something that everyone is using and everyone knows and say, right, can we make it run better on a rack if we know more about the rack, or the topology in particular of the rack? So in order to do this, and we started this project about 6 years ago, before a lot of this hardware was actually available, we built out what we called a CamCube. We built out a simple cluster it had 27 servers in it, and it uses a 3D torus topology. Now, you can think of a 3D torus topology as each server having 6 links out of it, wired to its neighbors to sort of form a cube, and then you wrap the top to the bottom, each side to each side. It's really widely used, and the reason why we sort of became interested in it originally was because these kinds of topologies are widely used in the high-performance computing community. And they have a number of nice properties. They have some downsides as well, but they have a number of nice properties. And we wanted to be extreme in CamCube. So what we said was, we're going to build a stack, a network stack on it, that will expose or really allow the applications running on it to really control the network. It's going to kind of meld the network and the application into one. You're going to expose the application logic to the network, and the network, in effect, is also exposed to the application logic. And just to show you how sort of extreme we were, all forwarding that is done within inside this CamCube is actually done in user space. So what does that mean? That means each time a packet comes in on one link, we shove it up to user space, we process it, and then shove it back out another link or handle it locally. This kind of extremity is sort of like, it's not how you would actually implement it in reality. You do a lot of this in hardware locally. But we did it in order to allow us to really understand what the benefits of this kind of approach could be. And so, I'm going to show you here a little bit about why we thought about this originally. So this is what a data center topology looks like today, where you have racks, you've got these top-of-rack switches, you've got a network, perhaps a higher level set of routers, and in order for a server to communicate with a server, you have to traverse many of these links. Now, if you build distributed systems, this is actually quite hard. And I said to you I was a distributed systems kind of networking kind of guy. So I spent a lot of time trying to build applications that ran on top of networks like this. And it's actually pretty hard. And it's pretty hard because what you have here is if you have two machines communicating here, they're actually going to communicate over many links here. And they have to cope with things like link failures, they have to cope with congestion, and they have no idea what's happening. So we thought, right, we'll get rid of that, and instead of that, we'll just connect servers to each other. We will remove all the infrastructure that run between it. Now, obviously, ideally, and particularly, perhaps even at a rack scale, you might be thinking, well, let's build a fully connected mesh. Well, of course, the problem with that is it's big. It's order n, where n is the number of servers that you want to connect. So instead of that, we looked at several topologies, ring topologies, tree topologies. As I say, this one is not very scalable, the full mesh. And in the end, we picked a hypercube. And we actually picked a torus. And we picked a 3D torus. And at the time, we thought, they're scalable. The node degree is constant 6. They're really fault tolerant. There's a high degree of multipath. So in order to get a message from that machine to that machine, there are loads of paths. So should a server fail or should a link fail, it has very little impact on the actual infrastructure. It's easy to wire. Because this topology has been used for ages by the high-performance computing community, they really know how to wire these things very efficiently. I'm not going to tell you today how to do it, but it's very, very well known. There is a trade-off, which is you end up with a higher hop count. So if this server wants to communicate with this server, it may have to go through 3 or 4 other servers to communicate. So this topology here looks very, very similar, or always very similar. It's the same as some of the topologies being deployed in the sort of rack scale type thinking. And what we did in our stack to sort of help open up visibility was to basically say, well, at the moment, in a topology like this, if this node and this node are communicating, they have really limited visibility of what is happening. So if there's a problem here, it's hard to understand what impact it will have on these two servers when they communicate. It's hard to infer congestion within the network, it's harder to understand what's happening. And so we started to build out a new stack. I'm not going to go into it in huge detail, but what I'm going to say to you, we sort of said, well, it would be much, much easier if you thought of this as a coordinate space with an x, y, and z coordinate. And nodes have a coordinate, and that's exposed to the application. And basically, if you have these two nodes, 1, 2, 1 and 1, 2, 2, it's really clear for the application running on here to understand what's going to happen. If I'm going to send a message to a neighbor, I know which link it will go on. And the servers have full visibility on the network, on the link status. So in this world, you end up with a world where you have a single routing protocol. So there's a single protocol that says how a packet gets from a machine here to a machine here. It's sort of point-to-point only. In this world, right, effectively, all you have is the ability to send packets to your one-hop neighbors in this network. How you forward them and the algorithms that you use are completely up to the applications that are running on top of the infrastructure. Now, within our stack, we provide many algorithms that you can use, but if you want, you can very, very easily implement your own. Also, on the any server that receives a packet is able to intercept it and process it as it would like, which means that you could change bytes in the payload, change bytes in the header. You could even transparently build caching layers that other layers wouldn't be aware of that are able to intercept and answer requests if they happen to have the answer. You get an awful lot of flexibility. And you can do things like caching and aggregation easily. Now, we built a large number of services on top of the CamCube. I'm going to talk a little bit about the MapReduce one next. We also built one to do with the graph processing engine. We built one about key value stores. We also built a vanilla TCP/IP service so that we could run any standard app that currently runs today on a cluster in a data center on top of the CamCube. But the one I'm going to focus on today is CamDoop, which is a MapReduce-like system. Now, I'm just going to give you a quick reminder about MapReduce, just so that we're all using the same terms and thinking the same way. I'm going to do this really quickly. So we start off with chunks, with the data chunked into chunks, in this one, 0, 1, and 2. Each one of these chunks is processed by a map task. And basically, what it will do is it will produce key value pairs. So say this was a list of words. It might say the word cat appeared 5 times and produce that as an output. These intermediate results are then sent through a shuffle phase, which moves the data to reduce tasks. And the idea is that all the same keys are processed by the same reduce task. So if this map task has produced a key value cat 5, and this one has also generated a key value cat, say 4, those two cats will end up at the same reduce task. They'll get combined, so that will become cat 9, and that will be output to the final results. And what we're going to do, yes. So, and the interesting observation, and this is where we sort of started from, was that usually the final results in MapReduce are much smaller than the intermediate results, okay? It's also the case that this shuffle phase is the bit that's really quite expensive. And in fact, if you look back in the literature, you'll see a lot of people were sort of motivated to do full bisection bandwidth networks in order to make this part efficient. So, given that the final results are often much smaller than the intermediate, the final results are often much smaller than the intermediate results. And in fact, what we see from data that Facebook published a few years ago was that 5.4% is the size of the final result compared to the intermediate result. In information published by Yahoo, the ratio is 8.2%. So, we began to think, well, if we're going to move something like Hadoop onto our platform, the obvious things to go after is the thing which is most constrained by the network, and can we exploit the fact that the final results and intermediate results are smaller, the final results are smaller than the intermediate results in the implementation. Now, I'm not going to tell you much about the implementation. I'm just going to give you a little bit of a flavor for one thing of it. But what I will say is that the goals were, we didn't want to change the programming model at all, and we haven't. There's no change to the programming model. We want to exploit network locality. So if two servers are close to the network, we want them to be able to exploit that in order to maximize the bandwidth that we have inside the cube. We want to get good server and link load distribution. We want things to be uniformly distributed wherever possible. And we want to get fault tolerance. We achieved all of these things in the design. And we have a paper that you can go and read. But the one thing I just want to give you a feel of is the bit which I think is the bit which really highlights how we exploited the network. So if you think of this, and we're not the first people to observe this, that if you've got these map jobs going to a reduced job, right, it would be great if you could use an aggregation tree. So in other words, instead of sending all the results to this single reduced job, right, wouldn't it be great if you could have some aggregators that took some of these results in and some of these results in and sent them to this reducer here. And this build this sort of aggregation tree. Now, the problem is if you take this kind of structure and try to map it to a traditional rack with a top of rack switch, what you end up with is these two servers wanting to communicate with this server, and this link here becoming shared by all the children. Now, I've shown it as just two servers communicating with one. Obviously, really, you'd like it to be more. But this link here becomes a bottleneck link. And so here, if we have these two communicating with this one, the link into that one will also become the bottleneck link. So what we did was we said, well, on something like the CamCube, we can actually exploit the topology. We could put aggregators and use the fact that on path you can manipulate traffic. And you can then have a node like this one, which is forwarding traffic from here to here, combine the traffic from there to there before sending it to there. And from here, again, from there to there, through this one to that one. You only have one link per child, and the packets are aggregated on path. Therefore, you get less traffic. Now, I'm not going to say much. Oh, so here we are. I've got an animation here. Two packets come in. They get kind. One gets sent. Now, I'm really not going to say much more about this. But what I do want to do is I want to show you the performance, okay? Because I think, this is the bit where it really began to convince us that trying to make sure that the sort of future topologies and the future hardware was exposed to the applications would have benefit. Now, we did this on an experimental test bed. It was 27 servers. They were organized as a 3x3x3 cube. It was using a quad-core Intel Xenon, 12 gigabytes of RAM. We used 1 gig networking for a number of reasons. And the runtime and services are actually implemented in C#. So actually, it's not that efficient. And what we did was we actually implemented CamDoop. We didn't take Hadoop because Hadoop is actually very inefficient. So we actually sort of hand implemented a new version of Hadoop, which is very efficient. So we could use that to compare the performance of it running on a normal rack with it running on top of a CamCube rack. And what we did was I'm going to show you some results. We did a workload sweep. And what we did was we looked at this ratio of output size to intermediate size for jobs, S. So let me try to explain that, because it's really important that you understand that before you see the results. So this is the intermediate results, and this is the output results. And when S equals 1, it means that the output results are the same size as the intermediate results. So this should be the point that is really the worst for something like the approach that I was talking to you, because what we were really doing was exploiting the ability to do aggregation on path. When S equals approximately 0, you get full aggregation. And what that really means is that each one of these intermediate sets of results has all the same set of keys. Different values, but the same sets of keys. So you end up with sort of the best aggregation happening which is possible. And I'm going to show you just 2 points in the design space. The first one is when we have R equals 1. So what this means is that all of the traffic from the map jobs is going to a single reducer. And on this time, we have the time to perform the shuffle and the reduce phase. So we're not looking at the time taken to perform the map job. It doesn't change between the two systems. And this is in a log scale. And on this side, I'm showing you the output size, the ratio between the output size and the intermediate size, where remember that 1 means that there is no aggregation and 0 means there is maximum aggregation possible. And obviously, being lower on this side is better. You want this to go faster. Being slower is worse. So the baseline, which that's basically running our code on a traditional rack with a traditional top-of-rack switch. And you can think of that as representing the world as is today. So then we just ran CamDoop, but we switched off all the aggregation. And as you would expect, the time to do this is actually constant, independent of this, because it doesn't really matter, the ratio doesn't really matter. You've still got to process the same amount at the reducers and do the same amount of shuffle if you're doing no aggregation. And this difference between here and here is the kind of difference of running with more bandwidth. So at the moment, we have 6 links, 6 gigabits per second. This was comparing to a 1 gigabit per second rack. So that difference is accounted for by just by the extra bandwidth that we have available. I would note that this is sort of, you have to think of this as the sort of the bisection bandwidth of the 3D torus rather than just 6 gig. But anyway. And that's the line when we switch on CamDoop, okay? So this is the line when we say this implementation understands the topology underneath it. It's able to exploit it. And as you would expect, at this end, it is getting the maximum benefits. In fact, over an order of magnitude. At this end, it's exactly the same. Well, that's what you'd expect, because this point here is no aggregation, and therefore neither system, the system with and without aggregation switched on, is able to benefit. And then what's interesting is if we remember that this is the ratio that Facebook talked about, so this is the ratio where they're working on average, we get a huge win. Now, that's with R equals 1. So that was with all the traffic going to a single node. That's really unfair. Well, it is a little bit unfair. It's not totally unfair. There are a number of apps where getting all the data back to a single node is actually pretty important. If you're doing things like search queries, you're very worried about getting the results back to a single node very quickly. But let's look at the other one. This is where we're going to do all to all. So we're now going to say that effectively there is a reduced job running on each server. There's a map job, and all that data has got to move. And again, I'm showing you here, on this side, the time in log scale. In this side, this value S, the output to intermediate size ratio. I'm going to show you several things. That's the baseline again, which is TCP CamDoop. TCP running on a CamDoop running on a normal switch. This is the CamDoop with no aggregation. That's just the impact of running on the CamCube. There is the performance of using CamDoop with the aggregation switched on. Again, we see the benefit at this end. And also, just to be fair, so this line here, if you actually look at it, it's actually worse than you would expect it to be. And it's worse because we're seeing sort of traditional problems that you have in a network. Our switch had incast problems and things like this. So I've also added here the theoretical line, the best you could do on a 1 gig switch. It's also fair to say that we have some issues with this, which would actually indicate that we could actually make this line go low as well. And there we go. Okay, so now, in the last sort of, I think, 5 minutes or 10 minutes, I just want to step back slightly. So I've talked to you about the hardware, and I've tried to give you a feel for how, if we take into account things like new network topologies and new in-rack fabric topologies, how we might be able to build out systems which are better. Now, and I know, one of the things here is to think about what are the opportunities and startups and things like this. So one of the things that I've learned in the last 5 or 6 years is that in order to really build out these rack scale computers. And in order to actually understand how to get the performance of the rack good, it takes a lot of what I just call these days raw IQ. There were a lot of really smart people that worked on this, for example, to make the performance of this good. On our rack scale storage, there were an awful lot of very smart people who worked on how to get the data layout, the right provisioning of the hardware in the rack in order to make it all work. Now, this is great. It's kind of good at one level, right? Because it means that it's very hard for people to come into this space because it takes a lot of knowledge, it takes a lot of understanding. But I think it also starts to give us a feel of an opportunity. And so one of the things I think is really exciting about moving forwards, and if you were to say to me, well, Ant, where do you see all this going now? Is that I think we're going to need better tools. We are going to need better things to support the building of the lower level software stacks and the hardware and understanding how the two interact. And I'm sort of coining this term automatic rack scale synthesis. It's basically based around the fact that there are an awful lot of complex choices to be made. So, for example, at the start of this talk, I told you about the Calxeda box, and I talked about how they had put switches in each of the processors to sort of remove the top of rack switch to actually move it into the servers. That's great. It reduces cost. It reduces overheads. What I didn't say to you was that how do you then pick the topology which they run over? And that was quite weird. It had 5 links coming out, 3 links in. How on earth do you know what topology that you would like to build? And certainly talking to some of the people who actually built some of the early boxes, like the one I showed you, it was a really complex problem. And in fact, many of them saw the topology that they were using as part of the sort of the IP that they were bringing to the game. And so, what we believe is that we really lack the tools. And, I guess there's this dream, which would be, wouldn't it be really great to give me a workload and to press a button and to have a rack fabricated to support that workload? And that's where I'd like to get to. Now, if you think of things like PCB building and you think of how we do things at the moment, there are a lot of tools which can really, really help. And I think it is feasible in the next 5 or so years to get to the point where we can do a pretty good job of, here's a workload, here's a set of hardware and a set of hardware descriptions. Please tell me how to put these together and tell me how I should actually think about the software stack that should run on top of it. Now, we're working on it. We're chipping away at the edges. So we started off by thinking, well, building these networks is really hard. Perhaps I can build a tool that will help me understand, given some hardware constraints and some hardware possibilities, the network that I might want to build to support my workload. We're also doing it now for storage. But let me just talk very, very quickly about the work on the in-rack fabric design. So this is joint work with Sergey, who is a postdoc at Cambridge and is absolutely awesome, and 2 colleagues from UCSB. And we know the network topology matters, and we also know that no topology fits all. If you've got network traffic that is sort of east-west, is going from server to server within a rack, you might want a very different topology to if you've got traffic which is going north-south, in and out of the rack. And we know that there's no one topology that works all. And so we've got this tool that basically, given a traffic matrix, so you could think of this as describing north-south or east or west traffic, and a set of physical constraints. And what I mean by physical constraints is, here are the processors, here are the number of links that they've got, here is the sort of basic properties of them. It would output a physical topology description. It would tell you the number of links per SoC that you should wire up. And it also tells you where these magic ingress-egress points are. So you've got this set of processors, they've got this fabric connecting them. Where do I put the cables that connect it to the outside world? And so we have this tool, and it's interesting because it can work. We can take workloads, It produces higher performance topologies. They have lower latency and less congestion. And it normally does it with lower costs. And I'm just going to give you, just to sort of close with, a feel. This is sort of all very much work in progress. But I just wanted to give you a feel for where we think we can get and why it's interesting. So this is a production data center workload. This was, if I remember correctly, a couple of hundred machines. So on the order of a rack in this new world. And what I'm showing you here is the latency between, so what we have is this traffic matrix. So we have the set of processors, or the set of things which are running on the rack, and we have which ones can communicate to which with each other. And what we have here is looking at the latency in terms of number of hops in the topology between them for two topologies. One is a 3D torus, which represents what you would go and pull off the shelf today. And the other one is for our generated topology. And the 99th percentile of traffic is 1 hop for the destination in the case where we've generated it, whereas it's about 10 for, it's about 8 or 9 for the 3D torus. And the other thing is we use 20% less links than you would in a 3D torus. And there's two ways of viewing that. One is we put less wires in, which reduces costs. The other way of viewing it is if we have a choice of SoCs, and the SoCs have different numbers of links on them, we can mix it up and say, well, in this rack, we'd like 20 SoCs with 1 link, and the rest of the SoCs to have 5 or 6 links. So on that, I'm going to sum up, say thank you. I'm happy to take any questions or comments or anything else, so I throw it open.
Any questions?
Okay, so Microsoft is obviously not into building servers as of yet, but so how do you plan on disseminating the results as an open source, or giving it to a hardware vendor to productize?
So really good question. As a research lab, most of the stuff that we output in public in terms of papers. We talk extensively about what we're doing. I think the question of how we get it a stage further is one that we're not yet able to take on. We're not yet fully convinced that I guess one of the things about having a foot in both camps is that you learn it's very hard to persuade people who actually do things for real and have many billions of dollars riding on decisions to do things. We're not yet at the stage where we can really convince people that this is the way forwards in terms of some of the stuff that we're talking about. I think the hardware changes, people are seeing happening. Whether we can convince people that we should be opening it up is yet still to be shown.
So I actually have 2 questions, but the first one is fantastic overview of the interplay between the architecture and the software components, but it seems that the comparison is perhaps a little bit unfair in that the trick part of the trick for the performance optimization of CamCube is the mapping of the MapReduce tasks to processing nodes in an efficient way. And the comparison with the traditional data center architecture and the issues with link congestion really are based on where you put the aggregation tasks, and that if the aggregation task is in the same rack, then obviously you wouldn't have that. So any comments on kind of opportunity to do a fairer comparison with the traditional architecture by trying to have someone play devil's advocate to CamCube by optimizing MapReduce for that architecture as far as the exact degree of fan out, et cetera?
So I think if you think of a traditional rack, so in fact, I think we've been quite fair. So at the moment, we're comparing across at a scale of a rack. So there's a top of rack switch with full bisection bandwidth between any 2 servers. The key point is whenever you do aggregation in a traditional rack, you send 2 flows of data to one. In the best case, the minimum you can do is 2 to 1 server. that bandwidth in is going to be split 50-50 between the two servers. And this is what people have found. So people have published papers saying, we should do aggregation for MapReduce. If you're doing it at a big scale, so you're thinking about running across many clusters, yes, there is often, and it's oversubscribed, particularly in the world when we used to be, 40 to 1 oversubscription. A lot of benefit with sending the data locally, even if it's inefficient. For here, right, if I actually switched on aggregation on the rack, the results would actually be worse than the results I'm showing you. So I'm actually showing you the best results we could get with aggregation or without, because without is actually better on this single rack. So the point where we were comparing is pretty fair. I do think, you might say to me, well, what about, you've shown me something that you've hand-rolled. What about Hadoop? We've also run Hadoop on the same rack. I can tell you that it's order of magnitude slower. It's badly, there's a lot of things about Hadoop which mean that you've really got to tune it. By taking our own implementation, we really went to the extreme of tuning it. And in fact, we can show you, I put on the one where the R equals 27, where we're actually doing significantly worse, or in the top of rack case than we'd expect to be. I actually showed you where it would get to in the perfect case. So I think we've been actually quite fair in that comparison point. Yeah.
Okay. And then the second question is the Intel announcement from last week with CPU and FPGA on the same chip that's plug compatible would seem to directionally point the way to your future architecture. So any comments on that in terms of kind of that degree of hardware level flexibility to implement custom designs?
Yeah, so it's really interesting because I think, often when I talk about this work and I talk about thinking about the sort of system architecture, right? People think of the sort of traditional co-design world. And the traditional co-design world for computer scientists is FPGAs and trying to understand which bits of your program you can compile down to FPGA and which bits you should just compile down to the commodity processor. I think these are kind of orthogonal, right? I think that kind of technology can be great. And if you can come up with compilers that can take parts of your code and compile it down to an FPGA to make it highly performant, I think that's awesome. I think the other challenge is to think, well, what is the actual architecture of this box rather than just what is the architecture of the processor? So for me personally, I'm not so worried about what goes on the silicon. I'm actually much more worried about how the bits are all plugged together and how we can exploit that for performance or cost. But I think the FPGA stuff is, I think it's awesome. And I think there's some great work from MSR. I think there's been some publicly talked about recently in a Wired magazine article which talked a little bit about some of the work we've been doing. And I do think that FPGAs hold great promise. But I see it as slightly orthogonal. I think both will happen.
I've got a question about your last point, the perspective you gave about optimized topologies. This seems to go, if I understood correctly, somewhat in the opposite direction than software-defined networking. Am I right in understanding it that way? And do you think that SDN is just not very useful for data centers, or that the technology is complementary to what you presented, and in what respect?
Yeah, I think it's completely complementary. So I think SDN is a great way of controlling a data center, an entire data center's network. What I guess when you get down to the rack level, right, it's a really interesting question about how some of this in-rack fabric stuff interacts with SDN. And I think that's a big open area. In fact, I have seen a slide deck from AMD where they actually list this as one of their challenges in this kind of space. As we get these in-rack fabrics, just what does the interface look like and why? I'm actually convinced for a number of reasons that we will see some control internally. You will have the ability, or you will have the desire to manipulate the network locally, and you will need some of that sort of functionality, whether it's SDN, whether it's some richer interface. SDN in some ways is quite limited in what it can do compared with what you might be able to do at a scale on a rack. So I think there's lots of open opportunities. Yeah, good question.
Any other? We still have time for questions.
like to have, several, let's say, data center architectures for different workloads, right? And MapReduce is definitely one of these workloads. What are the other ones that you can imagine that would require a significantly different architecture to get performance?
So I think the question that you're really asking me, and you're asking me the right question, right, which is partly a function of what do I expect the rate of change of the network to be? Now, if I thought of it as, well, I'm going to build a rack, and I'm going to stick some storage at the top, and I'm going to stick some non-volatile RAM in, and all these are nodes, there's a question about how, if I've got a compute cluster, what's the best way of connecting all that together? If I've got a storage cluster, what's the best way of storing all that together? If I've got an analytics cluster, what's the best way? But that's very static. That's I probably need 10 designs for the entire data center, okay? The other one to view is the one where, well, perhaps we'll come up with technologies, optical-based, MEMS-based, all sorts of things, that may allow us to reconfigure a rack at the scale of milliseconds to seconds as the workloads change on it. And then you can begin to think of, the sort of the rack where you upload things to it. I can look at how it's currently performing, and I can perhaps dynamically begin to optimize it to allow more performance, to free up bandwidth, to free up resources inside it. So it's a little bit depends on where we can get with the technology. In fact, at the moment we're looking at some very, very cheap backplane technology that will allow us to take something like a Calxeda box and to dynamically reconfigure the topology within it. And the trick is to do it very, very cheaply, and we think we have ways of doing it very, very cheaply, which will let us then change the pattern almost, with a few milliseconds delay. We'll be able to move from network A to network B. Okay.
Thank you very much.
Thank you.
Do we still have any idea challenge